Students are investigating balancing systems using the following setup. The students have a spring scale of negligible mass that is fixed to one end of a uniform meter stick, and the center of the meter stick is attached to the stand on which the meter stick can pivot. And there's a hook of negligible mass fixed to the top of this block of mass M0, and the hook can be attached to the meter stick through one of the small holes in the meter stick, as shown in this figure that I've been looking at. The students do not have a direct way to measure the mass of the block, and the block cannot be attached to the spring scale right here. So the students are asked to take measurements that will allow the students to create a linear graph whose slope can be used to measure the mass M0 of the block. So the question asks you to describe an experimental procedure to collect data that would allow the students to determine M0 and include any necessary steps to reduce experimental uncertainty. So the idea that it's asking you to understand is that the sum of the torques in this question, the net torques, the sum of the torques, wait, that was rough. The sum of the torques are equal to 0. So the net torque is equal to 0. And everything in this question is, or everything, this experiment is based on this principle. So I've drawn my meter stick here, and I can measure my force in this spring scale, and the meter stick is going to pivot around this pivot right here, and it'll rotate in one direction or it'll rotate in the other direction. So they hang the mass here like this, and that's going to cause my meter stick to rotate down. So how can I figure out what the mass, I'm looking for the mass of this block? Well, I know this force, and I know this distance right here. I know this distance right here, and if I look at this meter stick, I can find the different distances right here as well. And so that would allow me to once I know the force right here, the force times this distance is going to be equal to it's going to be equal to, when I hang this mass right here, for instance, it's going to be equal to mg, the mass that I'm looking at right here, m0g, times whatever the distance is right here, because I know that the torque is a force over a distance. Might not be able to see that. A torque is a force times a distance. And so I know that if I go like this, I have my force right here times my distance. That's going to be equal to the mass that I'm looking for times g times my different distances right here. So I'm going to call that, let's call this distance, I'll actually change colors. This will be my distance right here. So this is one distance, this would be another distance, this would be another distance. So this would be 10 centimeters, 20 centimeters, 30, and then 40 centimeters. So I can put in those different distances right here. And then if I would know my force from my spring scale right here. I know my distance right here. This is going to be 0.5 meters. I can solve for this variable right here by dividing by G and D. And so now I've described my experimental procedure to collect data. I would measure all of the forces for all the available distances. So I would measure for all available distances, for all the available small holes. And then I can use those distances to solve for to find M0. I can solve for M0 by rearranging this equation right here. So I hang the mass, I record the force. So let's see, I'll write it here. Hang mass. I would record the force. Once I've recorded the force, I know the distance. And I solve for m0. So this is part A. How could I reduce experimental uncertainty? Well, I would repeat this experiment for all of these different distances that I have right here. In part B, I want to describe how the data collected in part A could be graphed and how that graph would be analyzed to determine the mass of the block. So this is my equation that I used in part A. I know my distance right here. That allows me to find my torque, my force times my distance, and I know on the other side that these two torques are balanced, and so I have the mass of the block times g times the distance, how far away the block is from the axis of rotation right here. That will allow me to find my mass, and I repeated my experiment to find my mass. So if I want to make a graph, I want to think about this graph like this. I'm just going to make a slight change to this, my equation right here. I'm going to divide both sides by 0.5 meters, and so I have my force is going to be equal to m0 times g times the distance from the axis of rotation divided by 0.5 meters. And so if I look at this equation looks similar. I want to think about it like this. Y equals mx plus b, which is just the equation of a line. So if I graph this, I can put this on the y-axis. I can put this on my x-axis. So I'm going to graph my distance divided by 0.5 as my x variable. And then what is my slope of this line going to be? My slope, change colors here so you can see, my slope is going to be this right here. My slope of my line is going to be the mass times g. So this is the slope of my line right here. I'm actually going to, with the slope of my line right here, you probably couldn't see that, so I'm going to scroll down a little bit. The slope of my line, the slope is going to be equal to m0 times g. So when I graph this, after I get my slope, I'm going to divide by g so I can get this m0 by itself. So here's what I'm going to graph. I'm going to sketch my little sample of my graph right here. I'm going to put my F, my forces that I measure using my spring scale, on the vertical axis. On the horizontal axis, I'm going to put my distance that I measure right here, my distance from my axis of rotation, divided by 0.5 meters. That's going to be on my x-axis. And then I'm going to plot all of my different points. And then I'm going to draw a line of best fit. And then the slope of this line is going to be this right here. The slope of this line is going to be m0 times g. So how do I get m0? Well, I'm just going to divide I'm going to divide my slope by g, and that will give me the mass that I'm looking for. So my slope divided by 0, or my slope divided by g, is going to be m0. Let me just move that over so just in case people can't see that. My slope is going to be, or my masses can be found using that right there. So now, the students have an identical meter stick of mass m that's now attached to an axle that's fixed to a wall. Looks like this down here. So it's It's fixed to an axle. It's attached to a wall. The meter stick is free to rotate with negligible friction about the axle, and the meter stick is suspended horizontally by a string that's connected to a spring scale of negligible mass as shown in figure 2. So it looks exactly as it's described right here. So the angle theta that the string makes with the meter stick can be varied by attaching the string to one of the pegs along the wall right here. And the students use the spring scale to measure the tension required to hold the meter stick horizontal. So the meter stick stays horizontal. And they give us a table with a bunch of different measured values right here for theta and for the tension in the string. So the problem continues. It says the students correctly determine the relationship between Ft and theta is given by this equation right here, and they tell us that it's the correct relationship. We don't really need to worry about where it comes from. It says the students create a graph with this 1 over sine theta plotted on the horizontal axis. Indicate what measured quantity could be plotted on the vertical axis to yield a linear graph whose slope can be used to calculate an experimental value for the mass m of the meter stick. So if I have this equation right here, what can I put on the y-axis if I know that my x-axis has this on it? The way that I can think about this is by looking at y equals mx plus b. I know my x is going to be 1 over sine theta. So what does that leave me with in my equation? What does that leave me with in this equation? So if I look at this right here, what's left over? If I take this out, I have 5mg over 6. This is equivalent to this right here. So what can I put on my vertical axis? Well, this is going to correspond with my vertical axis right here. So what can I put on my vertical axis? I want to put Ft on my vertical axis. So on the blank grid provided, create a graph of the quantities indicated in part C that can be used to determine M. So on my vertical axis, I'm going to put Ft, and I'm going to divide this up into 5 equal parts because I have 5. I can see I have 5 horizontal lines here, 25, 20, 15, 10, 5, and 0. And now I'm going to graph this. And so the way I can graph it is by, this is going to be on my vertical axis. And on my horizontal axis, I'm going to have 1 over sine theta of this number. So I'm going to go to my calculator, and I'm going to, you can see I did it before, 1 over sine 22 is going to be 2.66. Notice when the first time I did it, I had my calculator in radian mode, so make sure that you switch it to degree mode because it's calculating it in degrees. And so I have 2.66 and my Ft is 21. So I have 2.66, let me erase that little mark there. 2.66 and 21, so it should be somewhere over here. And now I graphed all of this before in the interest of time, right here in Desmos, and it saved all of it actually drew a line of best fit. But the way that you would draw a line of best fit, in case you don't know, I'm just going to plot these points quickly here. I'm not really doing this exactly as it's supposed to look. And then I would put my ruler here, and I would just set up my ruler like this, and I want to put my line as close, I want to put my line of best fit as close as possible to all of these points. So it should look something like this, and I can graph my line of best fit, and that's how you do a line of best fit, just like that. And so now I can use this line of best fit to find to answer the last part of this question, which is to find my mass, the mass of that meter stick. And so I'm going to use my legit data over here instead of that sketched graph. So let me zoom in on this. And Desmos would do this for me, but I want to show you what it looks like without Desmos, because you're on the test you'd have to do it without Desmos, or you would have to be able to calculate it by hand. So it's good to be able to know how to do it by hand. So I'm picking points that are not part of my data that cross the grid lines of my graph here. And so this looks like it's at, let's see, this is divided into 1, 2, 3 fourths. That makes the math a little bit more challenging. So I have 19, excuse me. My vertical axis, I have 15, 16, 17, 18, 19, and on my horizontal axis, I have, if this is divided into fourths, it's going to be 0.125. So 0.125, this is going to be 0.5, no, 0.25, 0.375, and then 2.5. So it's going to be 2.375. 2.375. I'm just going to check that to make sure. My 0.125, or actually I guess I should do 0.5 divided by 4, because it's divided into 4 equal parts, right? Okay. And so now I'm going to find another point where it looks like it crosses. This looks good right here. Now we're at 10, so it's 19 minus 10. And then this is going to be 1.25. So minus 1.25. And so what do I get here? I get 9 on top, and I get, I'm showing my lack of mental math skills here. And so I get 1.125, so I get 9 over 1.125. This is my slope of this line, but my slope of this line is not quite the answer that I'm looking for yet, because I know that my slope of this line is actually equal to 5 over 6 mg, and I'm looking for m. So I know that this fraction is going to be equal to 9. 1.125 is going to be equal to 5/6 m times 10. And so I'm going to divide by 10 on both sides. So I have 9 over 11.25 is equal to 5 over 6 m. And now to get m by itself, I'm just going to multiply by, I'm going to multiply by 6 over 5 on both sides. And so these two cancel out, and I'm left with m. So my final step is going to be 6 times 9 divided by 5 times 11.25, and I should get, made a mistake somewhere. Let's see if I can find it. I divide by 10. That looks good. That looks good. Okay. So my final answer is 0.96 kilograms, which is the mass of my meter stick.